In this video, we will start talking about Chapter 4. Up to this point, we have not talked about any types of measurements or any math at all. But we are scientists, or this is a science class, and we are going to be using a little bit of math, talk about measurements. In science in general, we use the International System of Units, SI units for short. Obviously, this is a standardized system. It used to be that different countries had their own system of measurement and they were different, and it was difficult and cumbersome to convert from one to the other. And therefore, scientists got together and decided to use one standardized system for the measurements that we do. Most of the units that we're going to use, you're probably familiar with, but there are some that you may not be. The ones that we're going to be using the most in this course are going to be the ones that are listed in this table. Here's the base quantity, the name of the unit, and the symbol that goes with it. For the mass, the name of the unit is kilogram, then the symbol is kg. For length, the name is meter, and the symbol is m. For time, the name of the unit is second, and the symbol is S. For temperature, name of unit is Kelvin, and the symbol is K. Now, we are familiar, obviously, with the time in this country is the same, but the mass and the length are different. Here in the US, we use pounds instead of grams or kilograms, and for length instead of meter, we use miles. For temperature as well, instead of Kelvin, the Kelvin scale, we use Fahrenheit, so you may not be as familiar with the Kelvin scale. Maybe you're familiar with the Celsius scale, but we will talk a little bit more about the Kelvin scale in a few more slides. As we mentioned in the previous slide, the base unit for the mass is the kilogram. Let's make a distinction here between mass and weight. They are slightly different, although they're used interchangeably in everyday talk, but they mean two different things scientifically. Mass is actually the amount of matter that is contained in an object. So if I have an object three-dimensionally, how much matter do I have within that object, within that three-dimensional shape? It remains the same, so the mass doesn't change no matter where it is measured, because mass only measures the amount of matter that is contained. And obviously, whether I measure that on the moon or in China or in America, I'm not changing the amount of matter that is contained in that object. Now, weight is related to gravity. Weight is actually a force, and it's the force by which gravity pulls on an object. And it is given as the mass of an object multiplied by the acceleration due to gravity. And because gravity varies, so is dependent on where it is measured, therefore the weight of an object varies. The gravity is less on the moon, and so we weigh less on the moon than we weigh on Earth. The mass itself does not change because we don't change the amount of matter that is contained within a body, but the gravity changes and therefore weight changes. The base unit for length is the meter. The base unit for time is a second. These are the base units. Now we can combine base units with prefixes to write down a wide range of measurements. They can be very tiny to very, very large. And we can see measurements, right, from measuring things inside a cell, which are very, very small, in the order of nanometers or picometers, angstroms, the size of an atom. And then as we look towards the skies, the distances are so large that we talk about light years. They're so big. So we have a wide range of measurements, and we avoid writing really large or really small numbers by using prefixes in front of these base units to make our life easier and not having to write 15 zeros at a time. Here are the most common prefixes that we're going to use, from the largest to the smallest. Here between the kilo and the deci, well, there's a few more, but in between here in this table would be the base unit. So the base unit is 1. Instead of 1,000 or 0.1, it would be considered 1. That's my base unit. Note that if I have the prefix of kilo, so K, in front of my base unit, so I'm looking at 1 kilometer, meaning I'm looking at a distance because the meter is the base unit for a distance. And if I have a K in front of that, what that tells me is that I have 1,000 meters. 1 kilometer, therefore, has 1,000 meters. If I look to a unit that is smaller than my base unit, so everything that's from the kilo and up, these are larger units than my base unit. Anything from the deci and below are smaller than my base unit. So if I'm looking at a deciliter, the D stands for 0.1. So 1 deciliter, which is a measurement of volume, has 0.1 liters. So the D gets replaced with 0.1. So 1 deciliter has 0.1 liters. So on and so forth. Milli, which is 0.001 of my base unit. Millisecond. Second is the base unit for time. The M in front of it tells me that it's the milli, because that is the symbol. The milli then is 0.001 of my seconds. So if I have 10 milliseconds, I would have 10 times 0.001 seconds, and that would be 0.00 or 0.01 seconds, etc., etc. So I would once again suggest that you print this table out and that you become familiar with these prefixes and their symbols, because we are going to be using them, and also what they mean. So as you see them, because they're prefixes, obviously they're going to be in front of the base unit, and those letters, those symbols, correspond to certain numbers, and therefore we can replace that letter by the number that, and then still have my base unit, like the meter here, the seconds, the grams, etc. Let's look at an example problem. Express each of the following measurements in the appropriate units. So we have for A, 0.00163 meters. Now note that if I can move the decimal place to the left or to the right. If I move the decimal place to the right, it means that I will have a negative power of 10 when I write in scientific notation. Or if I am going to replace that those zeros with the correct prefix, the zeros here tell me that this is going to be smaller than my base unit, right? So if I'm looking over here, all of these are smaller than my base unit. So as I move the decimal point to the right, I can move it 1, 2, 3 times. And I can move it all the way to 16.3, but 1, 2, 3 times, that gives me 0.001. So 1, 2, 3, that is the milli. 1, 2, 3, that's the milli. So I could rewrite this 1, 2, 3, 1.63 millimeter. So mm, the milli in front of the m, tells me that is 0.001, and that's what I'm replacing out of this number. I can go to 16.3, but that gives me so 1, 2, 3, 4 times that I'm moving the decimal, and I don't really have anything here as a unit or as a prefix to replace. So I have 3, so 3 times 2, 1, I have 6, and I have 9, but I don't have a 4. So I can stop at 1, 2, 3, 1.63 millimeters. Now let's do this one here. How many times am I moving that decimal point? 1, 2, 3, 4, 5. Well, do I have anything here in the table that I can replace, basically move that decimal 5 times to the right? I have 3 here, and I have 6, but I don't have 5. So it's not enough to just move it to 5. I need to move it one more. 1, 2, 3, 4, 5, 6. And therefore, it will be 72.5. Then those 6 zeros will be replaced with a micro. So here it is, micro. 6 zeros. 1, 2, 3, 4, 5, and 6. And therefore, this measurement in the appropriate unit would be 72.5 micrograms. The last one, let's count once again. How many times can I move that decimal point to the right? 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have anything, I can't stop at 8, so I have to move it all the way to 9. And therefore, this becomes 89. If we look to what we have for 9 zeros, that is nano with the symbol N. So 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9. 89 nanoseconds, so 89 N, little n, S. Okay, now why don't you give these 3 a try? So we have for A, 0.0258 seconds, B, 0.0000639 meters, and C, 0.00000000054 grams. I will give you some time for you to work on these. Lastly, we are going to talk about temperature. There are 3 different temperature scales. We all are familiar with the Fahrenheit because this is what we're using in the United States. Most of the rest of the world uses a Celsius scale, which is based on powers of 10, so it's a little bit easier. Then the scientific world uses the Kelvin scale, and this is the SI base unit, the K. Now, To convert from Celsius to Kelvin scales is pretty simple. They are both based on, so from 0 to 100, really, based on powers of 10, but they have different starting points. If you look here in this picture, we have the Celsius scale over here and the Kelvin over here. Note that in the Celsius scale, water freezes at 0 degrees and boils at 100 degrees. So there's 100 degrees between the freezing and boiling of water. Then those 100 degrees are divided 100 times, and that's 1 degree. In the Kelvin scale, however, instead of 0, we start at 273 for the water freezing and boiling at 373 Kelvin. Once again, the difference is still 100, but we're not starting at 0, we're starting at 273. The neat thing about the Kelvin scale is that it starts at 0 Kelvin, which is also called the absolute zero, and absolute temperature. It's the temperature in which theoretically all motion ceases. They have gotten very, very, very close, but not quite completely at 0 Kelvin. Therefore, this makes the Kelvin scale a positive scale. So if 0 is the lowest possible temperature in the Kelvin scale, then everything else is going to be positive. This is not true for either the Celsius or the Fahrenheit. The conversion between the Celsius and the Kelvin scale is pretty easy. You notice to go from Celsius to Kelvin, all you have to do is add 273. So if water freezes at 0, then I add 273 to that, and that gives me the Kelvin equivalent. Water boils at 100, I add 273 to 100, and that makes 373, and that is the equivalent. Minus 273 is absolute 0 in the Celsius scale. Minus 273 plus 273 gives me 0 Kelvin. So all you have to do to go from Celsius to Kelvin is add 273. If you're going from Kelvin to Celsius, obviously you subtract 273. To Kelvin scale, the numbers are larger by 273. To convert from Celsius to Fahrenheit is slightly more difficult, or from Fahrenheit to Celsius. The difference comes from the fact that from the freezing of water in the Fahrenheit scale to the boiling temperature of water, there are 180 degrees. So every degree in the Celsius scale corresponds to 1.8 degrees of Fahrenheit scale. Plus, we also start, instead of 0, we start at 32, so we have to account for that. If we want to find the Fahrenheit, starting with the temperature in degrees Celsius, we multiply the temperature in Celsius by 9 divided by 5, or 9/5 is also 1.8. So you can multiply the temperature in Celsius by 1.8 and then add 32. To do the opposite, you take the temperature from Fahrenheit, you subtract 32, multiply by 5, divided by 9. Note that you have to do what is in parentheses here first. So you have to do the difference first before you multiply by 5 and divide by 9. If you don't put parentheses or hit enter in your calculators to complete the subtraction here, then it's not going to give you the correct answer. So be careful with this formula. All you need is just a little bit of practice with some of these formulas. We'll be doing a bunch more of these in class, but practice with your book as well. Here's an example problem or a sample problem for you to try. So normal body temperature in Celsius can go from 36 degrees to about 37. So express 37 degrees Celsius in both Kelvin and Fahrenheit.